So in this video we're going to look at finding the volume under a paraboloid using a double integral. So it says find the volume of the solid lying below z equals 4 minus x squared minus y squared and above z equals 0. So this means the z equals 0 means above the xy plane. And then what I want to recognize is that this right here, I can write this as z equals 4 minus parentheses x squared plus y squared. So that x squared plus y squared is giving me a paraboloid. The negation on it makes that a paraboloid opening downwards. And the plus 4 means it's been shifted up 4 units. So I have a downward opening paraboloid. I want the volume between it and the xy plane. And the other thing to realize is that z equals a function of x and y. So the next thing to realize is that I have my function of x and y here. If I plug in the opposite of x and the opposite of y, because of the squaring on the x and the y, I'm just going to get f of xy. And that tells me that the function, the paraboloid, is an even function and has symmetry with respect to both the xz and the yz plane. So I can actually use symmetry to simplify the calculation of the volume. And then I could ask the question, what does it look like? What does the region in the xy plane over which I'm going to integrate look like? And that just amounts to replacing z with 0. So 0 equals 4 minus x squared minus y squared means x squared plus y squared equals 4. So it's a circle of radius 2 in the xy plane. So we just look at this in GeoGebra real quickly. It can help us to understand what it is that we're talking about. So discard all that and then pop GeoGebra. Here's the paraboloid. Here's my x-axis, my y-axis. The intersection of the paraboloid with the xy plane is this circle here of radius 2. And as you can see, the paraboloid has symmetry with respect to both the xy and the yz and the xz planes. So if I want the volume bounded by the surface, the paraboloid, and the xy plane, I can actually calculate the volume in octant 1 and then quadruple it. 4 times the volume under the surface in octant 1. And that will simplify the calculation a little bit. So let's go back in and work this one through. So drawing the picture again, I have a paraboloid opening this up here at 4. It's opening down. And the trace in the xy plane is a circle of radius 2, and we would find that by setting everything equal to 0. 0 equals 4 minus, I can factor that minus out, 4 minus the x squared plus y squared. And then we add that x squared plus y squared to both sides. We get a circle of radius 2, so we know this is going to 2 and to 2. So if I want the double integral, if I want the volume under the surface, I need the double integral, and I need the surface under which I'm finding the volume, so that's the 4 minus 4r, 4 minus x squared minus y squared, and I can do either dy dx or dx dy. It isn't going to matter for this one. I'm going to go ahead and do dy dx, which means we need to get those upper and lower bounds of integration, and then we're going to need to multiply this integral by 4 because we're only going to calculate the volume in octant 1 and then quadruple it. So taking advantage of the symmetry of the paraboloid with respect to the z-axis. So what I need to do, if I'm taking the y slices, I'm going to be running from here to here. Y slices, I'm running from here to here. So I have to run parallel to the y-axis. So if I'm running parallel to the y-axis, I need to figure out the equation of this line as a function of x. So that would just be solve this circle for y. So we would get y equals, and we'd have the square root of 4 minus x squared, and we'd have plus or minus that. If we weren't taking advantage of symmetry, I would need both the plus and the minus. So if I weren't multiplying by 4 and I was dealing with the entire paraboloid running through all 4 octants, this would be the negative square root on this side, and this would be the positive square root on this side. So my bounds of integration would actually have to go from negative square root of 4 minus x squared to square root of 4 minus x squared. I'd have to run from the negative part up to the positive part. I'd be running my slices from here to here. So symmetry is nice because by focusing on octant 1, instead of having a negative square root on my lower bound of integration, I just killed my whole integration. Instead of having a negative square root down there, I get to have a 0, which is going to simplify my calculations immensely. So taking advantage of symmetry means I don't need plus or minus the square root when I solve for y. I just need that positive square root to go on the top. And then for the last integration, I need the line interval over which x is running, and it's going to run from 0 to 2. So that final integration is always over a line integral, sorry. Or interval. I said it correctly the first time. So this is the beast that has to be integrated. So if we're integrating first with respect to y, that means that the 4 minus x squared is held constant. This is a constant with respect to y. So on my first integration, I get 0 to 2. I get the constant 4 minus x squared times y minus, I know I have to integrate the y squared, so I'm going to get 1/3 y cubed. And this is going to run from 0 to the square root of 4 minus x squared. I probably want to think about it as being 4 minus x squared to the half power. And I haven't integrated with respect to dx first yet, so I have to keep the dx in it. When I put in the lower bound of integration for y, I'm going to get 0 cubed and 0 times this stuff. So that's all going to zero out. So I only need to plug in the upper bound of integration. So notice how my life is simpler right now. If I had negative the square root of stuff on the lower bound, I'd have to be plugging that into the integrals. And sometimes you have to, but if you can get away without doing it, it's nice. So you always need to pay attention to symmetry. So plugging in the upper bound of integration for y, what you want to notice is that you're going to get 0 to 2, and you're going to have the 4 minus x squared sitting here times 4 minus x squared to the half power minus 1/3, and when we plug 4 minus x squared to the 1/2 and cube it, we get 4 minus x squared, and it's going to be 3 times the half is to the 3/2 power dx. And this is to the first power. The base is the same, so this is really 2/2. So we also get 4 minus x squared to the 3/2 power here. So this can be, this first term, this product of this times this is actually just to the 3/2. And so I have one of them to the 3/2 minus a third of them to the 3/2 means that this is really, this whole mess just simplifies to 2/3 4 minus x squared to the 3/2, and it's a dx sitting there. And I just killed my stupid integral. Turn the eraser off. It's going from 0 to 2. This is a 2/3. There's the 3/2 power. The 2/3 is a constant. I can pull it out. And I've got to deal with this beast. And I could go dot, dot, dot at this point because this is just a single variable calculus integral here. But let's talk about it a little bit more because this isn't a trivial integral to have to deal with. So what I want to notice is that I've got a Pythagorean theorem form in here. And unless this form is showing up in that comprehensive table of integrals, it might be the case that I need to use a trig sub on this. So doing a trig sub, so create your right triangle with your angle theta. It's going to be hypotenuse squared minus a side squared. So this would be a 2 x and 4 minus x squared using trig sub. And then what I see from here is that the square root of the 4 minus x squared, so looking at this as being the half cubed. From here I get 2 times the cosine of theta equals the square root of 4 minus x squared. So if I want to know what this thing cubed looks like, this guy right here, 4 minus x squared cubed, so it's going to be to the 3 halves, would actually be 2 times, it would be 2 cubed, which is going to be 8, times the cosine cubed of theta. So this mess here to the 3 halves can be replaced with 8 cosine cubed of theta, and then we need to deal with the dx. So right here I would use, this side looks simplest, so this says 2 times the sine of theta equals x. So that tells me 2 times the cosine of theta times the derivative of theta with respect to x, so times d theta dx equals 1, because the derivative of x is 1. Multiply both sides by the dx. I can replace the dx with 2 times the cosine of theta d theta. So we would be replacing this 4 minus x squared to the 3 halves with 8 cosine cubed, and dx with 2 cosine d theta. So we're really getting a 16. We would be getting a 16 times 8 times 2 is 16 times the 2 that's already there is 32 thirds times the integral, and then it would be cosine cubed times cosine is cosine to the 4th power of theta d theta. And then what we want to do is convert those, convert the limits of integration over into theta world. So right here, this tells us sine of theta is equal to x over 2. So when we plug in 0 for x, we get when is the sine of theta equal to 0. That's going to happen when theta is 0. Replace the x with a 2. We're going to get 2 over 2 is 1. When is the sine of theta equal to 1? That's going to be a pi over 2. And now you've got a 4th power of the cosine that you have to deal with. So you can either use something sneaky. I don't think we have anything sneaky in our pocket right now. So I think in your comprehensive table of integrals, the cosine, the 4th power of the cosine isn't showing up. So we'd have to look at that cosine to the 4th as a cosine squared of theta times a cosine squared of theta, and then use the power reduction on each of these. So we'd get 1 plus cosine 2 theta, and it'd be times another 1 plus cosine 2 theta, and each would be over 2, so this would be all over 4, which would get factored out. And then you'd have to multiply this out, and then you should be able to integrate it. So it is dot dot dot, because it is just actually Calc 1 principles to integrate this, but it is a non-trivial integral to have to deal with.